I do want to make an announcement. Next week, the pro-section class is going to meet in the A&P lab Thursday at 11 o'clock and to prepare our male specimen for return back to WSU. And I told the students that in the first half hour of the time that we're in the lab that they can bring friends and family to check out the specimens to see what we've actually learned from them. And so if you would like to come in and take a look at our male specimen and check out some of his anatomy, he's very interesting. He actually has an enlarged spleen, has a couple of other things. Bladder's been more dissected out. You can find the seminal vesicles, and the prostate also has been dissected out. So it's kind of nice to come on in and take a look at the male specimen. Anatomy, of course, on the inside is the same except for things related to the sex. So I did want to invite you. If you are interested, you're more than welcome. So. Okay, back to our topic of spermatogenesis. What's important here is there's two processes that occur and one follows the other. Spermatogenesis occurs first and then spermiogenesis occurs second. So we have this little name at the bottom of this one, spermatogenesis, that's what's going to happen first, and spermiogenesis is going to happen afterwards. Because spermiogenesis is actually a grooming process to make the gamete capable of actually moving and penetrating and fertilizing an egg. It's important that we take a look at this cartoon of histology, and then we're going to go back to the bigger histology picture that we had earlier so that we can become familiar with how this structure should look. So I'm going to make a cross-section of a seminiferous tubule. And I want you to realize if I was to actually cut this and then lay it out, that we would actually have a situation that's almost like skin. And what I mean by almost like skin is that what do we call the first layer of our squamous cells? Stratum basale, that's right. And stratum basale are mitotically active. And this is the very same process that we're going to see inside our seminiferous tubule. We're going to have some cells sitting along this line that you can kind of think is that's the wall, and we're going to treat it in our mind a little bit like a basement membrane. So these guys are mitotically active, and they are called spermatogonia. So they're going to populate that area. There's going to be these cells, and if they're undergoing mitosis, remember from one cell we end up with two, correct? So I'm going to use this cell down here at the bottom, and from one I'm going to create two, and where am I going to put the second cell? I'm going to put it on top, correct? I'm not going to completely X this one out because we're going to keep one of the two cells at the basement membrane or at the wall of the seminiferous tubule. The cell that is moving towards now this area, which is the lumen of our tubule, the cell that is moving towards the lumen is going to be the cell that's going to become the primary spermatocyte. So from one cell, I'm now going to make a second cell, and I'm going to make the second cell a primary spermatocyte. It's like primary oocyte, always enters meiosis 1. So the primary spermatocyte has 46 chromosomes, and it's going to enter meiosis 1. But unlike the female, it's going to complete it. So meiosis 1 is going to give us secondary spermatocytes. And so I'm going to now put two cells here, and I'm going to call these guys secondary spermatocytes. These cells now are haploid. They have 23 chromosomes instead of 46. So primary spermatocytes, diploid, Secondary spermatocytes haploid. Secondary spermatocytes always enter meiosis II, and from these two cells, we'll end up with how many cells? In the egg, we end up with one. Now we're in the seminiferous tubule, and we don't hesitate. We go straight through. So we will go into meiosis II and come out meiosis II as spermatids. 1, 2, 3, 4. So from one primary spermatocyte, we will end up with 4 spermatids. And if the female system follow this, the meiosis like we traditionally do, this is a traditional meiosis process. If the female followed the traditional meiosis process, she would end up with 4 eggs. But that's not, and the eggs would be small. And the eggs would not be capable of a long trip into the uterus and implantation. So the female system does meiosis I and meiosis II, and the male system does meiosis I and meiosis II, but the female system is designed for only one ovum to actually undergo fertilization. The male system is designed to produce as many gametes as possible, because what we're going to find out is we will have millions, hundreds of millions of sperm actually deposited in the female reproductive tract, and only 100 or 2 will make it to the site of fertilization. And that's because all the barriers that are in there, and remember, we talked about previously that via the cervical canal, the woman is actually potentially in contact with the outside world. Her inside organs are potentially in contact with the outside world. So there's obviously a lot of barriers there to keep her from having infection or peritonitis in that aspect. So there's a lot of barriers our sperm cells have to overcome in order to actually get to the egg and fertilize it. So now we have spermatids, and that's what we have here. Spermatids are still diploid. Once you go into, spermatids are still haploid. Once you become haploid, you don't become diploid. And so spermatids are still haploid. They have 23 chromosomes and will now undergo spermiogenesis. Once you become a spermatid, we want you to be groomed so that you can end up being a viable sperm cell or spermatozoa. What I'm going to add to my drawing up above is I'm going to add a cell that is really unusual. It's called a sestentacular or Sertoli cell. And it's a really long cell. It starts at the basement membrane, and it goes all the way towards the lumen, and it has a long nucleus. I'm actually going to redraw that nucleus, because I'm going to draw it so that you can maybe recognize it from our histology. What I like about this that I've just drawn is the nucleus is big and long, and there's a nucleolus in this nucleus. That is a Sertoli cell or sustentacular cell. We'll get to that in the notes. But I'm just going to call him right now Sertoli because it's shorter and it's easier to say. So in the literature, you'll see it more as sustentacular, but a lot of people stick with the old Sertoli because it's so much easier to say. And I'm sticking with the old Sertoli. So in between all of these spermatogonia are these Sertoli cells. And these guys are going to be exceedingly important for the integrity of the seminiferous tubule, as well as the contents of the seminiferous tubule, as well as spermatogenesis. Because these guys are in charge of that entire process, even though we're going to talk about the hormonal aspect that's actually necessary for this. I'm going to erase this down here at the bottom so people really don't think that it's actually an important part of our topic. It was just used as an example. Now, With this in mind, spermiogenesis is going to create a spermatozoa. And take a look at these spermatids in our cartoon. Do they look like normal sperm cells? No. But they are ready to be gametes. They're just not looking right. And if they don't look right, they won't function properly. And that's what spermiogenesis does. It takes that spermatid, and we'll say early spermatid, this guy here, and causes a morphological or physical change of this. And the physical change is that one side will have a developing flagellum, and at the other side, we're going to end up with this enzyme packet called an acrosome, or acrosomal cap. It's an enzyme packet. And if you take a look down here, you see that that acrosome cap covers now the nucleus, and now we're starting to get a more recognizable flagellum, but there is a mid piece in this area that is full of mitochondria because you need to power the flagellum. So the mid piece is full of mitochondria to actually power the flagellum for our sperm. So going down into the writing material, let's go ahead and fill in the blanks. We've talked about the picture, and hopefully the writing will help you out with this. Spermatogonia, these are primordial germ cells, and that's why we say they're the outermost, because we're looking at the tube now, and so they're along the wall of the tube. You can consider them the most immature, because those aren't sperm cells yet. They are precursors to them, and these are mitotically active. And one of the two daughter cells becomes the primary spermatocyte. A primary spermatocyte always enters meiosis 1. And then goes all the way through it, no pausing, no hesitation, and completes it as a secondary spermatocyte. Our primary spermatocyte has 46 chromosomes. Our secondary spermatocyte has 23. Again, this is diploid, and this is haploid. The secondary spermatocyte automatically enters meiosis 2 and comes out as an early spermatid. From one primary spermatocyte, we will end up with 4 spermatids. The oocyte went through all of these processes, but the processes were designed to stop and wait for certain events to occur for completion. And in the female system, instead of having a cell that was viable, after the meiosis was done, we ended up with polar bodies. So polar bodies are the non-viable cell. That's just a packet of DNA as far as I'm concerned. Spermiogenesis is the streamlining of the spermatid. Because we want to go ahead and have these round cells to actually be able to be motile. And in order to do that, we need a flagellum. So what will happen is we will end up with a loss of cytoplasm. Then we'll end up with an acrosome over the nucleus of that cell. And this will make up the head of the sperm cell. Then the midpiece will be full of mitochondria for energy to power then the tail, which is the flagellum. So that's what spermiogenesis does. It makes a spermatocyte into a sperm cell. The sustentacular cells are the Sertoli cells. Cross-section of a tubule, see above. Because we already drew it, we had space, and so it also helps to explain the various layers that we actually see here: primary spermatocytes, secondary spermatocytes, and then spermatids, and then spermiogenesis occurs. So up there, what it's important for you to realize about Sertoli cells, these are exceedingly large cells that extend from the basement membrane all the way to the lumen. Basement membranes there at the tubule wall. When you hear the word sustentacular, what part of that word is something that you might know? Sustain, that's right. That's why they're calling them sustentacular cells, because another older term to help describe them was nursemaid cells. Because that describes what they do. They are the ones that actually promote spermatogenesis. And they are the ones that will also inhibit spermatogenesis. So Sertoli cells are nursing all of the primary spermatocytes, secondary spermatocytes, and everything along the process. They're helping to facilitate all of this. And without Sertoli cells, you won't have this process, because they are like nursemaids and they're feeding them. They're making sure they have the nutrients that they need for all of these processes so they can undergo these processes without interruption. The other thing that the Sertoli cells do is they form what's called the blood-testis barrier. What they do is, by doing this, they isolate the contents of our seminiferous tubules from the immune system. And let's talk about why we would want to do that. We don't want our immune cells actually encountering what's inside the seminiferous tubule, is basically what that tells you. Because when you take a look at our cartoon up here, what can you tell me about the contents of this that is different from all of the cells of that individual, except for red blood cells? Yeah, haploids. How many of your regular cells are haploid cells? Zippo. Well, does a haploid cell look like your cells? So that's the important thing. These are individual people one day, theoretically, right? Each one is its own half of a new person. And this half of a new person isn't the same half per se of the parent. And so the immune system, when it comes across these haploid cells, says, you don't belong in me, correct? And so the immune system will do what? Get him out of there. And so this is important, and this is the Sertoli cells are responsible for this. So the Sertoli cells help form the blood testis barrier to prevent autoimmune infertility. That's a big deal. Infertility would occur when you actually offed all those sperm cells, correct? So if you have something that breaks this barrier, in other words, the Sertoli cells aren't doing their job properly, you actually can end up with a form of infertility. This is not a common form of infertility, but is one of the causes of infertility for some individuals. The Sertoli cells also are responsible for secreting testicular fluid, and in this testicular fluid is nutrients as well as medium for transport of now streamlined sperm cells through the duct system. Let's take a look at some of the hormonal things that are required for the spermatogenesis and spermiogenesis processes to occur. More importantly, spermatogenesis. It's a hormonal process. Isn't that what puberty is all about? Puberty is all about hormones. Okay, so this is the brain testicular axis because the hypothalamus starts the entire process. So when puberty hits, the hypothalamus starts to release GnRH. GnRH stands for gonadotropin releasing hormone. Gonadotropin releasing hormone acts on the anterior pituitary to cause it to release FSH and LH. Well, this is the same with the female. Okay? FSH, follicle stimulating hormone, and LH, luteinizing hormone. So men and women both have gonadotropin releasing hormone, FSH, and LH. What's important is that FSH is responsible for stimulating spermatogenesis, and it does it indirectly by stimulating Sertoli cells. It says Sertoli cells, okay guys, we're going to make a bunch of nutrients, testicular fluid, and all that kind of stuff, and you are going to nursemaid these primary spermatocytes into spermatids, and then they're going to undergo spermiogenesis. So FSH tells Sertoli cells to do this. LH is going to stimulate testosterone production by stimulating interstitial cells. And you'll find this guy's name associated with this, Leydig. Interstitial cells of Leydig is commonly used, but interstitial cells are also a totally acceptable phrase. Interstitial is in between the seminiferous tubules. It is not in the seminiferous tubules, it is actually outside the seminiferous tubules, and in between all of the coiling up is where we'll find those interstitial cells. So once LH is released, we get testosterone from these interstitial cells. The important thing about testosterone here is high levels of testosterone cause negative feedback on GnRH release. This is important because there are some people out there that take exogenous testosterone. Endogenous means we make our own. They're made by us. We're making our own hormones. Exogenous means we're taking a product and administering it to us either orally or injection or something along that line. Who takes exogenous testosterone? Bodybuilders. So people who have this body dysphoria problem. You know, they want to be incredibly big and bulky as far as I'm concerned. So if they take testosterone, what does it do to their GnRH level? Tanks. What does it do to their FSH level? Tanks. So if we're not making sperm cells, what happens to the size of the testes? It decreases. What happens to their LH levels? Tanks, because they don't need to make any testosterone. Okay, so testosterone has a negative, high levels have a negative feedback on GnRH. So what this also should tell you is that men do have a little bit of a fluctuation of their testosterone levels naturally, correct? When more than enough testosterone is being made, then GnRH is going to go down, FSH and LH is going to go down, and then when that testosterone level reaches a what I call low enough level to no longer have negative feedback on GnRH will be released, and then testosterone will be released, and all that kind of stuff goes on. So this indicates that we have a slightly wavy, not a flat line of hormone in the system. This is normal. This is normal for thyroid hormone. All our hormone levels have actually, and insulin, for example, all of them have fluctuating levels to some degree. They also, as we learned with the ovary, have definite peaks when a whole bunch of cells are contributing estrogen to a process. So that's a little bit different story. The other thing about testosterone is it is required for Sertoli cells to really do their job.
If a man has like lower than average testosterone levels and he takes it like to supplement prescribed, does that help with spermatogenesis, or is it still inhibiting that?
So the question was, if an individual has, for some reason, low testosterone levels and takes testosterone supplementation to bring their levels up, what that will do is it will do these other things. It will help be an anabolic steroid, which is keep muscle mass and bone mass nice and healthy for that individual. It will help to maintain male sex characteristics, you know, the lower voice as well as the hair pattern, and it will help with their sex drive. But if you're taking testosterone, what's going to happen to your GnRH levels? They decrease. What's going to happen to your FSH levels? They decrease. And so it does not necessarily help with fertility. It helps with just an individual feeling good and well about themselves. So, and that's typically what people take it for. There's very few young men of reproductive age that have problems with testosterone levels. It's something that for some people gets problematic as we age. But most men actually have reasonable testosterone levels throughout their lifespan after puberty. So what does this tell you also about the fertility of a man compared to the fertility of a woman? 60, 70, 80 years old still can have children. Why they would want to, I don't know. But, you know, everybody has their own thing, right? So the fertility for men is throughout their lifespan ordinarily. There's always things that can interrupt things, but ordinarily, the fertility is present for men all through their lifespan. For women, fertility is from puberty to menopause. And so you have to realize when menopause hits, what do you think the gonadotropin releasing hormone levels are? They're actually high, and so LH and FSH levels are high, but there's nothing to stimulate. The ovaries are non-functional. Our oogonia have actually been all used up, because that's part of what menopause is. Menopause is you don't have anything that's going to work in those ovaries, even if you actually poke it with hormones, say, make something. We're out of them. You know, we don't have any eggs left. That's why some women have menopause at different ages. Someone will have early menopause and someone will have late menopause. And that's all related on as to how many eggs are populating the ovaries. And that's why that happens. But that's because oogonia for women don't stay active. Spermatogonia for men stay active. And when I say stay active, I'm talking about mitosis, because mitosis always gives you what I call your normal chromosome number of the individual. Yes?
After a while, does the body realize that there aren't many eggs and stops producing the higher level hormones, or does that continue?
No, that the higher levels continue throughout the remainder of the lifetime. So, and if they're trying to figure out if somebody's in the menopause, they'll check their FSH and LH levels. Because if the FSH and LH levels are high and they're not having any menstruation or anything along that line, that means it's menopause. But then the other thing you should always check is HCG levels. Because if you're not menstruating, sometimes you're pregnant. And there are women that think they're in the menopause and they're surprised and going to have a new child at home. And the siblings of the new child are surprised too. Okay. Inhibin. So the Sertoli cells, I hope you understand, are really super duper important cells. And they need FSH and testosterone to co-stimulate them to say, okay, let's everybody go ahead and go through meiosis 1 and meiosis 2. Let's make spermatocytes. So let's everybody do this. And spermatids, excuse me. But there is a time when the Sertoli cells will say, we don't need any more. We're full here. The N is full. And so Sertoli cells will produce a hormone called inhibin. And inhibin inhibits FSH release. You notice I didn't say GnRH release. I said FSH release. So what does this mean about LH? Still going. What does this mean about testosterone levels? Still normal. So let me ask you then, why would Sertoli cells want to say no more spermatogenesis? We need to stop this process, and I'm releasing inhibin to inhibit the release of FSH, so I'm not told to nurture these guys along. Why would we do that?
They're being used.
Pardon?
They're not being used.
They're not being used. Excellent. I also call it abstinence. So if you don't have the sperm cells leaving the system, they will build up. And the Sertoli cells are obviously there to make sure this happens at a regular rate. And when it says, wait a minute, we're not needing any more sperm cells, so they will release inhibin, and then FSH is not released, so Sertoli cells go fine and dandy. Testosterone levels are normal. This is very important because we affect spermatogenesis without affecting testosterone release. We'll make without a long time ago, when the procedure of vasectomy was introduced, many men did not want to undergo a vasectomy because they were worried about their testosterone levels. And they were reassured you can have a vasectomy and your testosterone levels will not be reduced. But it took a while for it to catch on and for them to believe, the people that were telling them, that this is actually really true. And this is why this can happen, because with a vasectomy, I talked about it previously, all you have to go in is find the spermatic cord in the scrotum and then make a little hole or a little incision into the scrotum, and you can easily find the ductus deferens, because it's a solid structure because we have to have peristalsis in it. And you can pull it on out. You can tie off two segments next to one another and cut right in the middle, and then let it go back into the scrotum and do you can do a single stitch if you want to. Many times people are very adept at it, don't even need to do a stitch. It all comes back together nicely. And what that means is we have removed the ability of the sperm cells in the testicle to leave, correct? We have cut off their portal of exit. And in doing so, because we know that Sertoli cells will now produce inhibin, we don't have to worry about any more spermatogenesis, but we will have adequate LH levels and we'll have adequate testosterone levels. And so this made vasectomies more popular when we're able to more scientifically describe why it was okay. Male sexual response. Two main phases here, erection and ejaculation. Erection is a parasympathetic and, interestingly, spinal reflex. So once it's started, this is a reflex. It will actually complete its action. And it's parasympathetic nervous system that is responsible for this. Because like in the female, with proper stimulation, parasympathetic nervous system is responsible for blood vessel diameter to the genitalia. And the parasympathetic nervous system is responsible for vasodilation. And so vasodilation means vascular engorgement of reproductive tissue and structures. And with this parasympathetic spinal reflex in men, it causes the release of local nitric oxide. And that is what is responsible for the actual vasodilation. So the parasympathetic nervous system causes the release of nitric oxide locally, and nitric oxide is going to be the potent vasodilator. With the vasodilation, what will happen is our corpora will fill, and the weight compresses venous outflow. So kind of like a pseudo tourniquet. So this is an unusual example of parasympathetic control of vascular BVs. And so medications for erectile dysfunction, the inability to achieve an erection or maintain or sustain an erection, is actually what the medication is. It's going to cause an increase in local nitric oxide. And the nitric oxide causes rapid vasodilation, which means rapid fill, and that rapid fill causes increased weight, which will compress the venous outflow. And that's actually how it works. In the days of old, they had many other ways to actually treat erectile dysfunction, and one of them used to be, and they actually still advertise it on TV for a lot of Medicare channels. That's what I know for old people channels. They used to actually, before medication for the nitric oxide release, they used to have a vacuum pump. And so the vacuum pump was placed over the penis and a vacuum was applied and blood would fill the penis. And then the second part that they had to do to maintain the erection was actually put like a rubber band type of unit at the base of the penis to keep the blood in the penis. And then that was one of the very first mechanisms that was actually employed for erectile dysfunction. You can imagine it wasn't very popular, but it was used before we had medication. And now we have medication, and they still sell those units on TV. Go figure. Somebody doesn't want to buy the pills, I guess. Ejaculation is interesting. Now, erection is parasympathetic spinal reflex. So once you get it properly initiated, it will complete itself. Ejaculation is sympathetic spinal reflex. Again, once you get it started, it will actually naturally complete itself. And what happens is the parasympathetic impulses reach a critical value. And we'll just say peak. And when they peak, kind of like our LH surge, you know, this causes, or estrogen, high estrogen levels causes an LH surge. This causes reflexive peristalsis in the duct system of the male, resulting in ejaculation. So parasympathetic impulses peak. This triggers a next event, which is a sympathetic reflex, and then peristalsis will occur and ejaculation is the effect. The refractory period typically follows that. Another erection cannot be obtained for a certain period of time, and what happens is we have resolution of vascular congestion. So in other words, blood is actually leaving, and this takes time. Before another cycle can be initiated. The older you get, the longer the refractory period. And for women, this refractory period is eminently short and almost considered non-present. And that's because the vascular congestion of the organs for stimulation is actually small, and blood leaves quickly and then fills back up quickly. Lengthens with age. Why would a refractory period normally lengthen with age? Yeah, this is pressure related, isn't it? As we age, what do you think about our vessels? Are they always as great as when we were younger? And so vascular integrity and atherosclerosis and diabetes and all that type of stuff actually will cause a slower fill as well as resolution of that. Any questions? Enough for sex right now? Okay, so we'll stop there and do some clicker questions, and you guys are out of here.